So what this is doing is ranking the way that structural particles interact with each other in terms of the resulting strength of the material itself that results. Okay? So you're sitting in a desk with a plastic seat. And the plastic seat is made of really long molecules. Really long molecules that have some non-polar parts and some polar parts. And the reason that the plastic holds together the way it does is because of the strength of attraction between those molecules. Those long molecules are attracted to each other. They have stickiness. Okay? And there are other kinds of molecules that have a different level of stickiness. But they nevertheless, they tend to stick together. So nylon is an example of a chemical that doesn't have a lot of polar places, but it still hangs together pretty well. It sticks together pretty well, makes nice structural materials. Okay? So what this does is look at some examples of chemicals, chemical formulas, chemical structural units, and how when you put all those structurals together into a structural material, how they behave, and we can rank those behaviors in terms of how strongly they react together, or how strongly they stick together. The resulting stickiness between those particles also relates to melting point and boiling point over here. Okay? So nonpolar covalent stuff, things that are molecules, have a structural unit we call a molecule. And so last week we learned to figure out when you have a polar or nonpolar molecule. Okay, Marissa? Let's sit up, please. Okay? Those nonpolar substances have very weak attractions that we call London dispersion forces. And last week we illustrated that with the shift in electron density, where we have electrons kind of grouped over on one side or another, creating a temporary polarity. It's weak, but when you put a lot of them together, or a lot of surface area together, it can create some pretty strong interactions. Now these are really small molecules, but really, really long chain molecules can stick together and make a pretty substantial structural material. For example, asphalt is just really long chain, non-polar molecules. But it's pretty substantial. We pave all our roads with it. That makes sense? Okay? Your skin, your hair, your fingernails is made of really long chain molecules. So the interaction between those molecules, the stickiness between those molecules, creates something pretty substantial. Okay? All right. But now these are really, really small molecules. So compared to the long chain molecules we're just talking about. Really small molecules. But you can see that this is a pretty low melting point. This is getting very near absolute zero. At absolute zero, all motion stops. And that's 0 on the Kelvin scale. It's negative 273.15 on the Celsius scale here. So that's pretty close to that. All right? It boils at not much further above that. Look how low the temperature is when it boils. Okay? And this is another nonpolar molecule. This is benzene. And it still has a pretty low melting and boiling point, even though it's a much larger molecule than that is. But there's a lot of stickiness between this molecule that doesn't exist here. Okay? But if we take all of these, this nonpolar molecule where you have those London forces caused by that temporary shift in electron density, a very weak attraction between particles, and we group them all together, then we can look at the boiling point, and the temperature range is right here on this scale, right in this range. Okay, and so this is on page 13 of your handout. You go to the next page, and the boiling point is grouped very closely together. So there's a very low boiling point, very low melting point, because the strength of attraction between the particles is weak. They come apart pretty easily. Okay? So I'm going to go back now to page 10 and look at the next category, polar covalent. We have to be able to figure out when a molecule is polar using those electronegativities and the way that the molecule is arranged. And these are all polar molecules. And if you average out the boiling point and melting points, these are slightly higher than those. Okay? It's not a huge difference, but it's a significant difference. Okay? So polarity, the permanent polarity, that's different from the temporary polarity here. The permanent polarity, these dipole-dipole interactions they're called. Okay? That permanent polarity means that the structural particles stick together with a little more force. A little more force. Okay? And so it's harder to pull them apart. A little harder than the nonpolar covalent. And so they have a slightly higher boiling point and a slightly higher melting point, because it's a little bit harder to pull those apart. Okay? All right, going back to 10 now, let's look at the next category. Ionic substances. Here's a couple of examples of ionic substances. And look how high these temperatures jump from where we were before. Huge jump in temperature there. Ionic substances are held together by the strength of opposite charges, completely opposite charges. Not particles that have temporary polarities, not particles with even complete polarities, where you have a positive end and a negative end of the molecule, but particles that are completely charged, positive and negative. Might be 2 plus or 5 plus, but completely opposite charges. Well, the strength of attraction between these kind of particles is much, much higher. Okay? And so, because it's harder to pull those apart, much harder to pull those individual particles apart, the structure that results from all those millions of particles together, the structure that results is even harder to get it to separate. And we have a much higher melting and boiling temperature. And when we melt something, what we have is we have particles that are, when they're frozen, they're stuck together, and we're trying to get them to start moving around each other. We have to add more energy to them. If they don't want to move, it's hard to do that. And once they're moving, then we've got to get them to separate completely to be a gas. And it's hard to do that. They don't want to do that because of those opposite charges. Okay? So the stickiness between those kind of particles is much, much greater, resulting in a much, much higher melting and boiling point. And then we get to that metallic bonding. And we looked at that last week. And we said the metallic bonding is the result of this electron C model, where the electrons provide a kind of glue that holds those individual metal atoms together, metal/ion atoms. Okay? You remember that? Mm-hmm. Talked about that? Okay. And those particles then are glued together with a great deal of force, but there's a huge range, a wide range in the temperatures, melting and boiling temperatures of metallic. And to help you visualize that, then I have these graphs over here, or these charts, that show the melting point here, where the metallic range is huge. But on the average, metallic is higher. It's harder to pull them apart on the whole, on the average, than most ionic substances. Okay? Ionic substances go right here. Metallic has this huge range, but the average is somewhere in here, much higher than that of ionic substances. Okay? And we have a similar behavior for the boiling points, where you got this really, really wide range of boiling temperatures, but on the average, they're higher than that of ionic. So it's harder to pull apart metallic particles that are glued together by that sea of electrons that's sort of holding the whole thing together. Okay? And lastly is covalent network. And we haven't really looked at covalent network, but covalent network is the result of particles that are atoms, okay, that are covalently bonded from one atom to the next. but they don't just stop with one. They keep going and going and going and going. Now I'm making this two-dimensional, but a covalent network is really three-dimensional. Okay? And going and going and going. Let's see, I might have shown you this one where we had Si bonded to O. Yeah, okay. So that's covalent network. The result of this sort of interlocking covalent bonding creates a substance. When you put them all together, the combined result of that is really, really hard to get it to pull apart. Okay? So those boiling and melting points for covalent network substances is higher than that of anything else. And so we look over here where I've sort of ranked them in this thing, and we can see this range right here is on the average higher than anything else. And the same for the boiling point. On the average, it's much higher than anything else in this chart. Okay? So you need to know that when you have these different kinds of substances, that the interparticle attraction is different for them, resulting in a different behavior of the substance. Okay? All right. So let's take a look for a minute as a couple of examples of the kind of thing that you might be expected to know. All right? So let's say I give you well, let's see, you wouldn't know that one. Sorry. Let's do this. I'm going to start over. I'm sorry. You wouldn't know about PCl5. Oh, let's see. All right, here are four substances. Here are four substances. And based on the behavior that we went through in this chart, and in this table, which you have in your unit handout, we need to try to figure out which of these are likely to have the lowest melting point and which is likely to have the highest melting point.
The lowest would be like the negative, right?
Well, I mean, it depends. Well, let's figure it out first, okay? Guys, shh, I can't hear the question, Sierra. CO, small o, big O, 2, parentheses, X. Actually, you know what? I probably should give you something besides that because you might mistake that for being an ionic compound. Well, it is covalent, but you wouldn't. If you looked at this as being a metal and a non-metal, you'd say, "Oh, that's got to be ionic." Well, I'm going to tell you up front it's a covalent. Okay, we'll do it that way. How about that? Yeah. So that's very wise to have out your unit handout. Well, we've got to figure out the classification of these compounds to figure out which one will have the lowest boiling point and which will have the highest. All right. So what Shane has noticed is this X right here. This X right here indicates that there's an unknown and almost infinite number of these structural units here. Okay, that's a typical way of writing a covalent network structure. Huh? Okay. What? Hold on one second. Let's label this, okay? All right. So what were you saying, Shane? Okay, but we don't want to do it that way. What we want to do is to figure out, is it polar? Is it molecular? Is it... But you're looking at the chart, you're just plugging in because of what's on the chart, right? Okay. All right, so this is polar, covalent, and it's a molecule. Okay. How about this one? Well, it's not on your list there, is it? How would you figure out if it's polar or non-polar? Well, if I don't do it, then how are you going to learn? Yeah, get out your pencils. Get out your test references. You didn't bring a pencil.
I've been writing a pencil for like 2 weeks.
The more you practice, the better you get at this.
Oh my God.
You gotta practice
You've already done enough practice. Well, I beg to differ. Guys, all right, so you have to start with the sharing, well, you start with the electron dot formulas, then find the sharing arrangement that best gives all the atoms the electrons they prefer to have. This arrangement gives both the carbons and the oxygens 8 electrons. That's that octet rule. Then you put it together in our Lewis dot formula, where the electrons that are shared between two atoms get squeezed in between those two symbols. Then you're going to take the sets of electrons and draw a structure here, a three-dimensional structure that gets those sets as far apart as you possibly can. And in this case, we have two sets of electrons around the central atom where the sets have 4 electrons. Remember, sets can be 2 electrons or 4 or 6. Okay? So the way, the arrangement, the three-dimensional arrangement that gets 2 sets as far apart as possible is 180 degrees. That's a linear electron pair shape. And so now we're going to replace the shared electrons with the atoms that go on there, and we have a linear molecular shape. Okay? Now, to get a polar molecule, you have to have 2 conditions, and you have to meet both of them. One of the conditions is that you have a polar bond. An uneven arrangement is the other. That's correct. But this is not uneven. This is an even arrangement. And so we already know, if you look at that we don't meet both conditions. Now the bonds might be polar. Haven't figured that out yet. You use the periodic table with electronegativities and do the subtraction for that. But it really doesn't even matter because it's got to meet both conditions, and it doesn't meet the condition of having an uneven arrangement. Yes. It might be polar then. Yes, that would be uneven. Okay? Huh? This has got to be nonpolar. So it's a nonpolar molecule. A nonpolar molecule. What kind of substance is this?
That's I need to see that.
That is ionic.
It had to be ionic, you got to have at least two elements. That's a metal. Well, there's nothing there. There's nothing down here. Right here. Right here. Todd, don't go there. Don't even try. All right. What kind of substance is this? Right here.
Ionic.
I got a metal and a non-metal. One of the two kind of formulas that you can tell is ionic.
I just feel ionic so long.
All right, ionic. So now all we have to do is rank these according to those different categories. And we'll have a reasonable idea. Not definite, but reasonable guess. Okay? To figure out what is going to be have the lowest boiling point. So which one of these substances then, by category, is likely to have the lowest boiling point?
The CO2.
Okay, lowest. Okay. Which one of these is going to have the highest?
Metallic.
Nope.
No, ionic.
It's the covalent
Nope.
network.
Covalent network's the highest.
But I thought it's
Oh my god.
Okay. So let's rank them in terms of numbers. This is 1 being the lowest. This is 5 being the highest. What's number 2?
No, it's the polar.
Polar molecules is 2. What's 3? Ionic is 3. 4 is metallic.
Would you put 2 in?
It's polar.
Right there above the first 4. Where is 4?
It's metal. Metal is 4. 2 is polar.
1, 2, 4, 5, 3.
Okay? That shouldn't be that hard. But, listen. What you have to know is that nonpolar covalent substances, molecules, have the lowest average boiling point and melting point. Polar covalent molecules have the next highest average boiling and melting point. Ionic substances have the next highest average boiling and melting point. Then metals have the next highest average boiling and melting point. And the highest boiling and melting point will be anything that's a covalent network. You can tell it's a covalent network by, usually, because the formula will have this parentheses and an X outside. Okay? Metals, well, you have to figure out if it's a metal. Okay? That just means going to your periodic table and finding where this is. Metal or non-metal. Periodic tables, remember, are sort of split into two main regions. We've gone through those regions. That's Unit 2 of your of this class. If you don't remember that, you need to go back and look at those regions of the periodic table. Anything on this side is a non-metal, except that hydrogen, we're dividing metals and non-metals, belongs right there. So it's also a non-metal. Everything else on this side is a metal of that stair step. That stair step is the dividing line. Okay? All right. So this is a metal. You need to be able to tell it's ionic. Ionic substances, ionic formulas, we can look at a metal-non-metal combination, or if the substance has a polyatomic ion in it with something other than hydrogen on the front. Okay? Anything with hydrogen on the front is going to be an acid except for water. Okay? But ionic substances, if it has anything but hydrogen over here, and it's metal or non-metal, then it's going to be, well, metals and non-metals, period, because hydrogen is not a metal. That's going to be ionic. If you have a polyatomic ion, and anything but hydrogen attached to it, you can assume that to be an ionic compound as well. Okay? And any formula with hydrogen on the front, we're going to assume in this class to be an acid. Okay, that makes sense? So that's the way this works. Would you like to give me to give you a little practice quiz?
I think.
No.
Are you going to grade it?
I don't know.